All right, so moving on to section 7.3. So we're going to do some more things with what we've been doing in 7.1 and 7.2, but we're going to look at sampling distributions and the central limit theorem. Remember, a sample we define as a smaller subset of the population because it's not always practical to survey or find values from every member of the population. Okay, so we're often going to compute or find numerical summaries of some sort of samples. And it might be multiple samples of differing sizes. The most commonly used notation here is going to be the sample mean. And we're going to call that X bar. It's an X with a bar over it. That's why it's called X bar. So here are some qualities. If X bar is the mean of a simple random sample, of size n, drawn from a population, because remember the sample is a subset of that population, with mean mu and standard deviation sigma. Three things are true. The mean of the sampling distribution, we're going to call that the mu of the X bars. So it's the mean of the sample means, basically, okay? But that is going to trend and get really close to just the overall population mean, okay? So remember, when there's a subscript on any of our variables, it means the mean of whatever it is that the subscript says. So number two, the standard deviation of the sampling distribution is going to be sigma sub X bar, okay, or the standard deviation of the X bars. That's what that means. The formula for this is going to be the population standard deviation divided by the square root of n being the number of values in the sample. And then thirdly, the standard deviation that we just mentioned where we have sigma sub X bar is sometimes what we call the error. It's sometimes called the standard error of the mean. In other words, it kind of describes how far off the standard deviation from our smaller sample is than the overall standard deviation. Okay. So kind of maybe some newer formulas. I don't think they're really that difficult to figure out. So let's do one where we practice maybe finding some of these. So if a population has a mean of 6, and a standard deviation sigma equals 4, then I want you to find these new things. I want you to find the mu of the X bars and also the standard deviation of the x bars for a sample size of 25. All right, so firstly, if I want the mu of the standard deviations, it's going to be the same as the regular old mu. Okay, and that was given to be 6, so that's what that is. However, the standard deviation of the x bars is going to be whatever we had for standard deviation and then over the square root of n. Okay, so we were given 4 for the population standard deviation, and we're going to put that over the square root of 25. And so we end up getting 0.8. Okay, so pretty easy formulas to figure out. Remember what I said, any formula like this you'll be given on a test, you just have to know how to read them. You have to know things like mu means average, and standard deviation is the sigma letter. All right, so if you have a population that is what we call normal, in other words, it's normally distributed like we've been talking about, then the sample mean is also normal. And that's for any size set, any size sample. All right, so let's define, though, what the central limit theorem says. So the central limit theorem kind of defines some terms first. So let x be the mean of a large sample. We're going to define a large sample as anything bigger than 30. Okay? The sample does need to be simple random. Remember, we defined that back in chapter 1. That just means that every value is equally likely from the next value. So if we have a large sample that we chose in a simple random format from a population, from a bigger group, in other words, with mu the mean, and standard deviation sigma. As long as we can show that these things are true, then x bar follows a normal distribution also. So in other words, we can make determinations about this smaller set. We like it when things can be called a normal distribution because we can say a lot of things about them. They have very specific patterns. Okay, so x bar follows a normal distribution with the following formulas at play. The mu of the x bars will be mu, just like I mentioned before, and the standard deviation of the x bars will be our formula above as well, which is standard deviation divided by the square root of n. So, if I want to compute probabilities using the central limit theorem. The central limit theorem simply tells you when you're allowed to assume that there's a normal distribution and when you're not. Okay? When it's a normal distribution, we can find the z-score and we can use the chart that we've been using over the past couple of sections. Okay? If it's not a normal distribution, you can't do that. But this is going to include things as long as n is bigger than 30. Okay? So the first thing is you need to make sure that the set is big enough. Okay, so make sure n is 30, and if so, we can use the normal curve. Step number 2 is you're going to need to find the mean of the x bars and also the standard deviation of the x bars. Okay. As always, we can sketch a picture of the bell curve if it helps us, if we're more visual. So I'm just going to say sketch a picture if necessary. So maybe at first you'll want to sketch a picture, maybe after that you feel confident and maybe you don't need to. And then last but not least, use the table, the A.2 table that we've been looking at for a while to find the area. So what the central limit theorem says is that we're allowed to treat bigger sets as if they were a normal distribution, okay, even if we weren't told ahead of time that they were. And so it's actually really nice. It allows us to do a lot of the same things we've been doing in the last two sections. So a sample of size 75 will be drawn from a larger population where you know that that population has a mean of 10 and a standard deviation of 12. Okay, but let's say that we don't want to take data from the whole population. Okay, we only want to take a sample size of 75 because it's easier, right? But the question is, do we lose accuracy if we pick a smaller group? Okay, and the answer is, as long as the set is big enough, you can usually just treat it as if it were a normal distribution. So I want you to find the probability that X bar will be between 8 and 14. Okay, so in other words, what's the chances or the probability that my sample size of 75 is going to have a mean between 8 and 14 when all of them together, not just the 75, the whole group, had a mean of 10? Okay. All right, first requirement is you need to make sure that the sample size is greater than 30. And it is, right? 75. Okay, and once it is, you can determine what we can expect the mean to be. So the mean of the sample means, basically, is going to be the same as the overall population, or 10. The standard deviation of those sample means is going to be your standard deviation for your whole population and then over the square root of your n, which in this case is 75. So I'm going to want you to use 4 decimal places for this. Okay, usually 4 decimal places will lead to a final answer that is rounded enough. Okay. So once again, I'm going to pull up the formula for z-score. Remember, z-score is value minus mu over standard deviation. Okay. So what we're trying to do is we're trying to find the probability that the sample mean will be between 8 and 14. Okay. So let's find both z-scores. So the z-score for X bar equals 14 is going to be Z equals value minus expected mean over the standard deviation that we just found. Notice it's not the standard deviation we started with, it's the standard deviation of the means, because that's what we're talking about here. Okay, so this works out to be 2.89. And so you look at your chart and figure out the value at 2.89, and I think the proportion there is quite high. It's 0.9981. Think about it this way. If we want the values or the probability that the value stays under 2.89, that's going to be a lot, right? Because we're really, really far over to the right. And then the z-score for X bar equals 10. Not 10, right? It was 8. So that z-score is going to be found by doing the same formula. Looking for my whiteout. So the z-score for 8 is going to be z equals 8 minus 10, and then again over that 1.3856. Okay, so if you do that calculation, you're going to get about negative 1.44. And again, look at your chart, your table. The proportion that matches up with negative 1.44 is 0.0749. So let's answer the final question. So the probability then that the mean we come up with, if we take the 75 values, is going to be between 8 and 14, is going to be these two probabilities subtracted from each other. Okay. So kind of explained in another way, and I hope you'll listen to this explanation. This is what's happening. Let's say the population includes 100,000 values, okay? We don't have the time to break down 100,000 values. So in this problem, we chose a sample size of 75. But depending on which of the 100,000 values or whatever it is I just said we choose, depending on which 75 we choose, we might be getting different means along the way, right? Like if you average 75 numbers and they're different from each other, like this group of 75 is a different 75 values than this other group, then you might expect different means. But no matter which 75 values you choose to talk about, there is a 92.32% chance that the mean for those values you chose would be between 8 and 14. Okay? And the reason, by the way, for that is because we were expecting the mean to be about 10. Okay? So we went out from 10 to include 8, between 8 and 14. All right, so let's do another percentile question. So what if I tell you to find the 15th percentile of X bar? Okay. So remember, this is where you know the area and you're trying to match it with the z-score. So this is where you look at your chart. The closest value to 0.15 on the chart is 0.1492. Which corresponds to a z-score of negative 1.04. Okay, and then this is when you take the z-score and you put it back in that formula. So z-score is going to be x bar. Notice it's not x this time. We're trying to find x bar. So it's x bar minus the 10 and then over that standard deviation we've been using that we found. So again, cross multiply and then add the 10. And so the 15th percentile of sample means we would expect to be about 8.56. Okay. In other words, if we chose a random 75 values and we got a mean of 8.56, we would have had a higher mean than 15% of the other groups of 75. Okay, that's what that means. All right, so let's look at another example. So let's say that the IRS reported that in 2010, the mean federal income tax paid was $8,040, okay, per household. Okay, so notice that would be everyone who paid taxes, so that would be the population. And let's assume the standard deviation is 5,000. But obviously, if we're talking about everybody who filed a return in 2010, that is a lot of people. That population includes a ton of people. Okay, so let's say that the IRS wants to study people further, so it draws 1,000 random tax returns to look at. Okay, something you might not know about the IRS. They don't look at everybody's tax return. They don't have the manpower or the time to do that. Okay, what they might do is you just might get you might be part of the unlucky 1,000 that they choose to look at a little closer. Okay, and then they try to figure out, you know, are these people filing their taxes correctly? Okay, so surprisingly, you can actually fly under the radar and maybe still not be being honest on your taxes for quite a long time. But once you're on their radar, by the way, you're really on their radar. Like they'll audit you every year after that if they think you're kind of on the dishonest list, if you will. All right, so I want the probability that the sample mean tax paid is less than $8,000. Okay, remembering that I could choose any 1,000 tax returns, right? Out of the millions of tax returns that would come in 2010, I could choose a lot of different groups of 1,000. Okay, so what's the chances that any of those groups of thousands I choose would have means that were less than $8,000? Okay, so the first thing is, I mean, you need to mention this. The sample size is definitely bigger than 30, right? It's at 1,000. Okay, so we can use a normal distribution. You might have some questions on Math Connect where it says, is it appropriate to use the normal curve or not, like before you ever get started? And if the sample size is not bigger than 30, you're just going to choose no, and that'll be the end of that question. Okay, but this time the sample size is plenty big enough, right? It's definitely more than 30. So if we want our average of our groups of 1,000, it's going to be equal to or close to the original average, which is 8,040. Okay, but the standard deviation of those means is going to be whatever the standard deviation of the whole group is, and then over the square root of n. So it's going to be the 5,000 I was given, and then over the square root of 1,000. So again, we're going to use 4 decimal places here. So I get $158 and then 0.1139. Okay, so let's figure out the z-score. So the z-score for x bar being 8,000, which is the value that we were asked about, is going to be z equals that value minus the overall mean over the standard deviation we just found for the means. Okay, and that equals about negative 0.25. Okay, notice we need 4 decimal places here, but here we always just need 2 for z-score, because if you remember, your chart only reads 2 decimal place values anyway. So the probability here, make sure it says less than, right? We do want the probability that it's less than 8,000, so I can just read the chart as it is, because the chart, again, always reads less than. So what you would find on your chart with a z-score of negative 0.25 is 0.4013, okay? So in other words, there's about 40% chance that any 1,000 people we pick are going to have a mean that might be less than 8,000, even though we expected the mean to be about $8,040. All right, so question B. What is the probability that the sample mean tax is between 7,600 and 7,900. Okay, so we've done problems like this before a lot, right? We just need to find z-scores for both of these values. We need to look to see what proportion that z-score matches up with, and then we're going to subtract the two. That's the gist of what we're going to do. So first, let's find the z-score for x bar equals 7,900. Okay, so we're going to do value minus the original mean over the standard deviation of the means. Okay, so I'm going to let you maybe figure out what that is. Okay, so that's going to be something, right? And I want you to pay attention to what that is. So maybe take out your calculator, maybe pause the video. And then I want you to match that with a proportion from your chart. Okay, so if you do this on your calculator, make sure you put parentheses around the top. But if you work that out, you're going to get a z-score of negative 0.89. And then you read your chart there, and you'll get a proportion of 0.1867. Okay, so let's do the z-score for the smaller value. So it's 7,600 minus the 8,040, again over the 158.1139. Okay, if you work that out, you're going to get negative 2.78. By the way, both of these z-scores were negative because these are both smaller than what we were expecting. We were expecting 8,400. So look on your chart, and that proportion is very small, 0.0027. Okay, so in the end, you're going to subtract them, right? So let's write out a statement here. The probability that X bar is between the 7,600 and 7,900 is going to be these two subtracted from each other, 0.1867 and 0.0027. The difference between those is 0.81840. All right, so let's throw in a percentile question. So let's say I ask you to find the 40th percentile of the sample mean. In other words, find the mean that 40% of the sample means would have to stay under or have to be a little bit more than. So remember, anytime we want percentile, we're just looking for area. So you're looking for the closest value in the middle of your chart. The closest value to 0.40, okay? So maybe pause and take a look at that, but that is going to be 0.4013. That's the closest thing to 0.40 we have on the chart, which corresponds to z equals negative 0.25. Okay, and then you take that negative 0.25 and you solve for what x bar would need to be. So x bar minus 8040 over the mean we found, or sorry, the standard deviation we found. So cross multiply, add the 8040, and so we can expect the means, 40% of the means are going to be less than this exact quantity. Okay, notice we round to the nearest penny when it's money, not the nearest dollar. Okay, so the last two questions of this section I really want you to pay attention to, and I want you to take really particular note that these two last questions are asking two different things. So part D, first I want you to tell me, would it be unusual if the sample mean were less than 7,500? Remember, 7,500 is quite a bit less than we expected, right? We expected 8,040, okay? So I want you to skip a little space. I want to ask these two questions together and then we'll answer them both. The second question is it unusual for an individual to pay less than 7,500? Okay, the key there is that in the second part I'm asking for an individual. In the first question in part D, I'm asking, would it be unusual for the 1,000 tax returns that the IRS chose to audit for them all to average less than 7,500? Whereas this one, I'm just asking for one individual tax return. Okay, so it's definitely a different question. So let's tackle part D first, and then we'll talk about how part E is different. So the z-score for x bar equals 7,500 is going to be z equals 7,500 minus 8040, and then over the 158.1139. Okay, just you getting a z-score of this amount in general should kind of make you pause and think, that's a little weird, right? Because notice our z-scores usually aren't that large. Okay, so z-scores usually stay, 3 or under. Okay. So let's look at this. I wanted to look at the chart here. So notice negative 3.42 is really pretty tiny, right? So it's going to be 0.003. Okay. So the matching proportion with this one is 0.0003. Okay, I think I missed an O when I said it before. So yes, this is really unusual. Okay, this is unusual. And remember, it is unusual because it's less than the 5%. Okay, if you can show that it's less than 0.05, then it's unusual. Okay. So for 1,000 people to have that low of an average of a tax return, or sorry, not a tax return, but a tax owed, would be unusual. Notice this one asks for an individual. Okay, this does not mention sample mean. It's not a mean of a bunch of tax returns. It's a mean of, not a mean, it's one tax return, sorry. So this does not mention sample mean. So in other words, we're just going to use the standard formula here. We're not going to use our standard deviation of the means, okay, because we're not talking about that this time. So when we go to find z-score for an individual, x equals 7,500. Okay, it's subtle, but notice I'm not saying x bar because that's not what I have. Okay, it's just plain old x. Is going to be 7,500 minus the 8040. And then all over 5,000. I don't put it over the 158.1139 because it's not a sample mean. Okay, and notice this equals negative 0.11. Okay, and if you read that from your chart, that's much more likely, right? This corresponds to a probability from your chart, which is 0.4562. Okay, so notice this is not less than 0.05, okay, which means it's not unusual. In fact, it's actually kind of likely, right? It's 45% likely. So, so no, it is not unusual. In other words, it's usual that that would happen. Okay. So make sure you read the difference. There was a difference in Part D and Part E in the fact that Part D asked for what's the chances that a mean would be less than 75. This is asking for an individual. Okay, so again, we're just using the chart quite a bit, and you're just kind of learning how to read these problems. So make sure that you're using proper notation when you take your notes. When we're talking about x bar, it's the mean of the x's. When we just mention x without a bar, it means the x value individually itself.